warm in here. All right. So speaking of that, now we can move on. Like I said, today we're doing two topics. Because they're the last topics in circuits, they're the last topics, and that means they're the hardest topics. Um, Remember what the last topic of static electricity was? Gauss's law? Yeah. All right. So this one is not easy either. Okay. So it really requires your utmost attention. Um, it's kind of tricky. It starts off easy, it gets a bit more tricky. What's really tricky about this topic is not the theory behind it, but the problems that go with it. Okay. So the theory behind it is actually quite simple. Is once you get into the examples, they get a little bit more tricky. Okay. Let's start. This is PowerPoint number 18 and capacitors. We're going to start there. So we're talking about capacitors now, and we're shoving those into circuits, and we're trying to find all the things that you guys can possibly imagine, and just put those into circuits and see what happens. That's basically what we're doing. Um, Capacitors are what? What do they do? What purpose do they serve? They store charge. What's that? They store and release charges. That's exactly what you need to know about capacitors, and this is exactly what they do in a circuit, all right? Now, you might get charge from plugging your device into an outlet, but you might not need it all the time, right? So if I'm something plugged into there, do I need those charges right now? Not necessarily, all right? I might need to build up those charges to be able to do something. What's really cool though about capacitors is I can plug it in, charge my capacitor to a level that is higher than what that gives me, right? So what I can do is I can build like a dam, right? So a dam is going to collect water flow, all right? And then it's going to release it all at once so you can get a mega water flow all at once because you want to do something really that requires a lot more work. And that's basically what capacitors can do as well. If let's say you need a lot of charge to something that requires a lot of energy, for example, is back in the day, you know those camera flashes? Yeah, those, right now it's easy. Just flash an LED and whatever. It doesn't require that much work. But back then, they were used to require so much energy to be effective that they would actually blow out the light. So they would have to like change the light bulb each time they took a picture. And so what happens is you build up the charge and then you rush all those charges at once in a moment into the flash of into the light bulb, and that'll flash. It'll burn out after, but you'll get your big bright flash for that fraction of a second that you needed when you're taking a picture. All right. So that's useful for many things. We're going to talk a little bit about what the uses are for that. Let's move forward. We're going to learn how to calculate the charge and apply all this stuff, calculating current, voltage, all that for capacitors in series and in parallel. And here you go. This is what they look like. Capacitors, in this case, they could be drawn in two different symbols. That's the first one. It could also be drawn as just these two parallel plates like that. Okay? Just make sure you know that these parallel plates are equal in length, whereas if you look at the battery, there's a small one and a big one, and the capacitor is two of the same size. Okay? This one's going to be in series. This one's going to be in parallel. So far, so good? Now I have to ask you, which one of these is going to hold the greatest amount of charge? What do you think? The parallel one. Why? You're right. The answer is the parallel one. Okay. You're right. You can charge them all at the same time. It's not the fact that they charge at the same time that makes it have more charge. I want you to imagine that this one has a charge Q, this one has a charge Q, and this one has a charge Q. And if you think of these as currents, when you discharge them, these charges are going to go in this direction. And at this point here, you're going to have the accumulation of all three charges, right? So here you would have 3Q charges. Whereas here, if you have Q charges here, then that Q charge is going to go here, and that Q charge is going to go here, and that Q charge is going to continue. So the overall charge in the left case, in the series case, is just going to be Q, whereas the overall charge on the parallel side is going to be 3Q. The charges, they'll add up. Okay? So there is this important equations that we need to know. The first one is actually the most important one. Q is equal to C times V. Do you guys mind if I just put down the blind here? All right. So the first one is actually the most important one, and it's the one that you're familiar with. We did a lab on this, right? That charge is equal to the capacitance of your capacitor multiplied by the voltage that you pass through it. Okay? And your capacitor will probably be constant, and so therefore you can regulate the amount of charge that goes onto your capacitor by modulating the voltage. I'm not going to explain that one anymore. It's also the most important one out of the two. This one here is the energy stored in your capacitor. So don't forget, energy is what's doing work, right? Work is what's driving anything. If you're lighting up a bulb, it's energy that's doing it. It's not current that's doing it, it's energy that's doing it. And to calculate the energy in a capacitor, it's pretty simple. It's this one equation here. We'll use it once today, but it's not that important. It's just a matter of knowing that equation, being familiar with that equation. But by and far, the more important equation for today is that that the capacitor has a charge Q that is a measure of its capacitance and its voltage. Okay. So a parallel circuit with capacitors, we're going to call these circuits C circuits because they're containing capacitors, and resistor circuits, we're going to call them R circuits. And later on, we're going to do something called RC circuits, which is kind of like a combination of the two. So parallel, right? So parallel capacitor circuits are a great way to create something with a charge that you needed to have. All right, and the more you have in parallel, the more charges you can store. It might take more time to charge them, but ultimately you can charge more stuff at once. And similar to what you learned in resistors, if you had I'm going to draw it up here, if you had a circuit with, oh, I ran out of space. Just redraw this. I'm going to draw it over here. If I had a circuit with capacitors, Kirchhoff's law still applies. And Kirchhoff's law, if you remember, or one of his laws, was that the voltage across a parallel portion of a circuit is going to be equal. Oops, should be 0 here. Right, so the voltage drop across each capacitor in parallel is going to be 0. That's the exact same thing as what you learned at the resistor, right? And if we have that voltage dropping across our capacitor, and we have our capacitance, we can calculate basically the charge on each one of these, right? Because we have the voltage, we have V, we have C, and therefore we can calculate Q, right? And if every single one of those have the same voltage, well, that's really convenient. Right? Let's see what we can do. So we have this equation here, that the capacitance, the total equivalent capacitance, is going to be equal to C1 plus C2. Now, how do we get that? So I said that each of these capacitors are going to have a charge Q. We can call them Q1 through 3. All right, so Q1, 2, and 3. And you can say that the total Q is equal to Q1 plus Q2 plus Q3. So on and so forth, forever and ever and ever. All right? And we know that the voltage doesn't drop across each one, so we can now figure out what the capacitance is for each, right? So if we were to say that it's the voltage multiplied by everything in that equation, right? This is going to give us the total equivalent capacitance, right? This one's going to give us a capacitance 1, this one's going to give us capacitance 2, and this one's going to give us capacitance 3. and so on and so forth. So we can say that in order to determine the capacitance of a parallel circuit that has many capacitors in parallel to each other, you can simply add up the capacitance. Yeah. Yes, you're right. You're right. It's Q divided by voltage. Okay. So far, so good. So here it is. And each one of these capacitors is going to have a charge Q. This is going to be Q, this one's going to be Q, and this one's going to be Q. And when they come together, they have Q total. And in order to find the equivalent capacitance or the total capacitance or the parallel capacitance, you just add them up. And so you would say that CEQ is equal to the sum of all capacitance I from I is equal to 1. If you wanted to write that in summation notation, right? That would be the formula. Yeah. Because you can have an infinite number and it wouldn't matter. The formula stays the same. So far, so good? I feel weird teaching you guys in a hospital. If I went back and I looked at this, I want you guys to draw a parallel. When you, I get it, parallel. I want you guys to draw a parallel and think of resistors in parallel. Okay, when you think of resistors in parallel, you add resistances how? What was this, the formula for that? Yeah, 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3. In the case of capacitance, does this look more like the series formula or more like the parallel formula for resistors? Series. Okay, so let's take a look at what series capacitors now look like. So all the capacitors in series store the same charge, right? Because they're charged by induction. And I'll explain what that means. So if I have, let me just switch to yellow. Okay, if I have, not yellow. Okay, here's a capacitor attached to another capacitor, attached to another capacitor. All right, and they're in series together, which means that they're connected with one end to the other. And I charge this first capacitor at the top, and it's going to have 4 positive charges. So what's going to be the charge on the plate that it's right next to? 4 what? 4 negative. Great. Where do those negative charges come from? The what? Exactly. So don't forget this plate, or sorry, maybe this plate and this plate are attached. They're literally the same. They have a connection in between. There's a wire. So that means by induction, these negative charges went up, leaving behind a positive charge in the bottom plate. Now, what's going to happen to right here? What's going to happen right there? It's going to be negative. How negative? 4. So it's going to have the same charge again, right? And the same thing here. We just continue going. And the same thing here. So as you can see, like whatever the charge of this first one is, it's going to be the same as the second one, and it's going to be the same as the third one. And however many charges there exists of capacitors in series, it's going to be equal regardless. All right? So now we can say that, and this here, what does this look like here? V is equal to V1 plus V2 plus etc. That's another Kirchhoff's law, right? The fact that the voltage drops across each one. So if we know that, right, and we know that the charge is the same across each one, we can make this equation happen right here. Because each voltage is going to be equal to some charge Q over its capacitance, right? So let me just write that here. V is equal to V1 plus V2. Each V is going to be equal to Q, and it's always the same Q, over the specific capacitance. And so if I have an equation that looks like this, Q is equal to C equivalent is equal to Q over C1 plus Q over C2 plus Q over C3, et cetera, et cetera, et cetera. Well, I can cancel all my Q's. And if I cancel all my Q's, what am I left with? 1. So I'm going to have 1 over CQ is going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3, et cetera, et cetera, et cetera. What does that look like? Resistance in parallel, all right? You see, it's kind of the opposite of what you studied when you did resistors, right? So we can write down a formal equation here. So 1 over CEQ, or just rather CEQ, CEQ is equal to the sum of all capacitances I from I is equal to 1 to N. That would be the equation for series capacitor. So far, so good? There's the equation. I kind of like wrote over it. But I guess you get the point. All right. Knowing all that, now we can do some problems. Determine which of these from lowest, or from, it says from largest, right? From largest to smallest, the equivalent capacitance for the circuit. All right, take a second to do that. I want to hear your answer. All right, what's the equivalent capacitance for A? 3. Very good. What's the equivalent capacitance for B? 6. What about for C? Okay, so now we easily can place them in order because it's going to be B is greater than A greater than C. Let me rephrase the question now to change it up a little bit. Rank these in order from highest to lowest in terms of the charges stored. What is the charge of C? Q. What is the charge of B? And the charge of A? All right, now we can rank them, right? So B is greater than A is equal to C for charges. All right? What's that? Okay, so remember when I was explaining, I said that in parallel, the charges, let's say each capacitor has a charge Q. Well, they add up together when the parallel part ends. So if you add up the two together, you get 2Q. Whereas here, the charge of the first one is going to be the same as the charge on the second one, right? So coming out of here, it's still going to be just Q. Okay? And the same thing for the first one. All right. Find the equivalent capacitance. Go ahead, do that. All right. Now I'll give you a hint. It's very similar to finding the equivalent resistances. First, you do anything that's in series, then you move on to anything that's in parallel. Okay. Go ahead, do it. Which two capacitors or which three or whatever many capacitors are you going to combine first? 5 and 20, exactly. So you're going to combine these two first into a capacitor of how many? 4, exactly, 4 microfarad. Once you're done that, you take this new one and you take it together with these that are in parallel. And that one's going to be 30. And now these two are in series, so you can add them together, and that's going to give you a final total equivalent capacitance of, has to be lower than both of those, 20. Yep, exactly. Okay? Let's do some more examples. So you were supposed to build a 15 microfarad capacitor. You made a mistake. You only have 5 microfarad capacitors to your disposal. How are you going to wire them in order to get 15 microfarad capacitance in total? Yeah, very simple. Wire them in parallel. Exactly. Wire 3 5 microfarad capacitors in parallel. Yeah. Next example, very similar type of question. You have 3 capacitors. How can you arrange them to give the maximum or the highest amount of capacitance and also the lowest amount of capacitance? So for highest, you would use parallel and least. Okay, good. You guys are looking at me like, is he asking us these simple questions? Is it just me? Well, here we go. Actual examples with numbers. So here's a question I want you guys to work at is, first of all, determine the equivalent capacitance. All right, once you have that, I want you to find the total charge on each capacitor. In order to find the total charge on each capacitor, you can do it like we did with current. All right, so remember that current splits up in a parallel circuit, and so does charge. Charge also splits up in a parallel circuit. And after the parallelity part is done, when the circuits come back together, then the charges should add up against that total charge. Okay? So knowing those two, solve this problem. So I know the voltage here is 45 volts, and here it's going to be 45 volts. Here it's going to be 0 volts, and here is going to be 0 volts. All right, keep going. Yep. If you stick with microfarads, then your answer is going to be in microcoulomb. And that's only if volt stays volts. It's always safer to convert everything back to the original unit. It's always the safest way to do it. Yep. Come on, Suzanne. Yep. Exactement. Okay, let's talk about the answer real quick. So what we can do here, on the right, we have the voltage drop in one capacitor. That's mega simple, all right? So 12.5 microfarads multiplied by 45 volts. Someone give me a number for that. What did you get? Yeah, 562.5 microcoulombs, okay? I left the micro there so I can put it back into my answer. If you want to prevent making any careless mistakes, I would just convert it into farads and volts, right? Because I can't make that unit conversion if I had, let's say, millivolts. If I had microfarads and millivolts, what is my answer going to be in? Then you can't do that anymore. So it's always safer to just convert them into farads and to volts. Now here, I have a total equivalent resistance for those two capacitors at 8.33. All right, so I did them. I did the 1 over C1 plus 1 over C2 is equal to 1 over C total on the left. And so now I can find the charge on the left because the volts is 45. The capacitance is 8.33. Can someone give me a number for that? 375, not 3.7, 375 microcoulombs. All right, and that's the total charge across both capacitors. So what is the charge on each capacitor? It's the same. So remember, the charges on the total on a series capacitors is equal to the individual ones in that series. So it's going to be 375 microcoulombs and 375 microcoulombs for this one too. Yeah. All right. In case you forgot on how to solve these, I have a little bit of a procedure here. This is for later on when you might have forgotten how to do this. You come back to this slide to figure out what you did. We talked about this, how capacitors in series are charged by induction, right? So the first one charges the second one, charges the third one, therefore they all have the same charge. And now we can do some more complicated problems. I want you guys to do this in groups on the walls. So example 4, example 5, and then we'll come back after that, okay?
Est-ce qu'on leur donne leur tableau qu'on veut là? What is it? Tourner? What is it? No beans? You get nothing to do, you're worth nothing.
Ouais, mais il y en a plus d'autres. Ouais, ben, il y a une crayon. Ouais, ben, t'en as. Ah, t'en as deux. Ouais, c'est déjà gentil.
Il fait, genre, justement, genre, c'est chill. Genre, il n'y a pas, genre, de la bonne conscience, ben, il est déjà assez gentil, une bonne entreprise. Comment ça, il va aller? Moi, je vais pas sauter comme la merde, on va sauter à sauter. Franchement. Non, on fait pas l'équipe, regarde.
On fait une méga équipe.
Ils ont des forces. Allez, give me pass one so I can charge. Il faut juste trouver ton charge après ça. C'est ça? C'est pas ça? How much charge goes to the battery? C'est ça, j'ai total charge. Non, mais si moi j'ai écrit total charge, ça marche tout ça, non? Total charge. Je sais pas, mais en même temps, c'est ça. Parce que ça passait lui. Ah ouais, c'est ça. Donc, tu fais 4 fois 12. Non, mais je pense que c'est 88. Ouais, ça arrête là. Ça arrête là. Ça arrête du bon sens. Ok, après ça, find the charge reach capacity. Charge. Là, tu sais que c'est 4.8 qui va se séparer avec ces deux-là. Okay. Tu fais 2 fois 3. 24. 1.5. le total charge, mais ça va être juste par rapport à la université. Ça fait pas qu'elle en fait.
Faudrait qu'on confirme ça avant de commencer.
J'ai fait une charge sur son site.
Ok, c'est Tano, c'est le 22.
Exactly.
22.4. Donc, ça, c'est faire la diminution.
Ouais, parce que genre, la charge de ça, c'est exact la charge de ça, et ces deux-là sont en série.
2 fois 12, ça fait un 4. 1.5 fois 12, ça fait un combien?
Mais tu pensais les multiplier, genre là, ça fait de 4, c'est égal à 5.
Yeah, you do that. That's the answer?
22.4.
That's the total charge. Do this right here.
That's the thing, because they're in series, right? So technically, the charge of this one should be the same charge as this, right?
Exactly.
Okay, so if the charge of the first one is 48,
Why would it be 48?
no? Ah non, ça serait. Faudrait qu'on trouve faudrait qu'on trouve le voltage drop.
It's not 48. I'll tell you that. It's not 48.
Faut qu'on trouve le voltage drop ici pour trouver la charge. Où on trouve le total charge de ça c'est 42, right? Tu vas entrer par là, mais c'est 2. 2 fois 12, c'est égal à combien?
On a trouvé la charge de ça, genre c'est Q égale à genre C fois V. Et genre on fait ça. On a les votes restent les mêmes.
The voltage drop here, after the voltage minus this, I bet that is the same here.
24 divisé par 4, c'est quoi? 22.4 divisé par 4. J'ai la petite montre avec la calculatrice.
5.6.
Sérieux?
That's right. You have to find the voltage for the 4 microfarad capacitor.
This 5.6 volts. Après ça,
That minus 12.
je fais 5.6 fois, attends, 2 est égal à
Est-ce que c'est 5.6?
No, it's 12 minus.
11,2.
Listen to Sammy.
11.5.
Exactly. Listen to Sammy and Danielle. Yeah, because that one's in series with the battery. So it's going to get all of the charge.
C'est 12 moins 5.6. 6.4, 12 moins 5.6. Ah, mais si, parce que ça fait. Ok, ouais, il est 205, c'est pas négatif. Ok. C'est la même chose.
j'imagine, les gens dans la maison. Genre vraiment.
C'est la pause, on s'est dit. Donc, c'est plus en pause.
Find charge on capacitor when close the charge. C'est ça? It's the same thing? Non, non, mais c'est pas le but.
Non, le but, c'est vraiment
Ah, that's it.
All right, ready for the next one?
Yeah. Yeah.
I need to erase that.
J'ai eu des problèmes avec les gens de batterie.
Je peux essayer quelque chose. 500 plus 750. Ça fait combien? 1250. 1250. 1 sur 1250 plus 1 sur 100 à la moins 1. Ça donne 9,03. On en a donc 1 sur 9.
Can I steal some of your markers here? I know you have more than one.
Après ça, total charge, donc on fait 15 fois 9,03.
Erasers? Where are the erasers?
Il y a genre 5.4 là-haut.
Ah, tu veux l'écrire?
Ouais, c'est en série. Genre, pour le 1 Q, pour les deux, genre,
On fait 135. 55. Non, je fais 135.4. Divisé par 100.
Yeah, you find the voltage drop here and there.
135
And there.
par 100.
Now you get the voltage there. And
Là,
now
tu fais un peu plus long. Tu fais 135,4 moins 1,354. Non, tu fais ça, moins ça, right?
you have to
Ça,
find.
c'est un voltage drop. Je veux savoir c'est combien de voltage.
No, you have to find the voltage drop here too. You have to find the voltage drop here too.
135 moins
pourquoi vous ne pouvez pas juste genre 135.4 fois 500 sur 750 sur 1250 pardon. La proportionnalité, j'ai fait la proportionnalité genre.
15 moins 1,354
Bah oui,
moins 13
oui, voilà. C'est la proportionnalité qui fait 135.4
Puis ça donne
fois 500 sur 1250 fois 500. Vu qu'ils vont se séparer dans la charge va se splitter pour les deux.
But we don't know the charge yet until we find it there. Ouais, that's true. That's true. Yeah.
Ok, là, tu trouves c'est quoi le voltage drop versus en faisant ce calcul, c'est qui le voltage représente et capable de savoir c'est quoi le voltage.
la même chose. You're doing a proposal.
Là-dedans. Oui, c'est pratique, vous savez bien le sucre.
You're gonna mix resistance and capacitors.
That's what we're doing after the break.
Are we gonna have problems with two batteries?
Maybe it's a bonus. Maybe it's
Oh yeah.
Non, tu veux trouver c'est combien de voltage tu vas utiliser là-dedans. Parce que sinon, tu vas essayer d'utiliser tout ce voltage qui passe. Donc, tu enlèves celui après aussi parce que c'est juste ça qui est utilisé.
You see, you have the amount of Charles Series output the same. Oh wait. The same capacity. Wow, because I think your calcul is more takes into account all these things.
Moi, je pense que je vais prendre le silver.
1.354 nanana.
Moi, tous les petits standards, genre, je trouve que c'est rendu beau, là, avec le standard. Oui, mais celle-là. Mais celle-là, je la change. J'ai demandé, ma mère, c'est mon. Je pense pour Noël ou ma fête, là, elle est comme, si tu veux la regarder comme une je suis comme des mini boules en or, là, comment c'est? Fait que j'attends. Puis j'ai des boules en or, là,
25$, je vais prendre les me faire chercher ça.
ça m'a coûté 23$ avec, il me dit si j'achète boucle d'oreille, le changement était gratuit. Là, elle me l'a repercé parce que le trou était pas tout petit. Donc là, elle me l'a repercé comme ça n'a pas fait mal. Mais ça a pincé un peu, mais c'est genre. Alors, j'ai les affaires. J'ai dit à mes parents que je voulais m'en faire un autre, puis ils m'ont dit que c'est pas un autre.
Ouais, it's true. Yeah, you're right.
Je vais t'en faire un autre coup.
Soit ici, soit
Moi, je
là-dedans.
trouve qu'à travers,
Ouais, mais
c'est.
mon père, comme je te donne l'argent chaque semaine, c'est pas pour te payer tes piercings. Je suis comme, mais j'ai travaillé cet été, genre, de l'argent, comme, c'est pas grave. C'est nous qui estamos sur le site, on va te
Si j'en
l'enlever.
fais un autre, j'en ferai un, genre.
Ouais, mais j'allais m'en faire un autre dans 2 semaines, là, mais. J'allais en faire un autre dans 2 semaines.
One half
On peut aller.
Je vais te dire que Kelsey, elle va se faire passer la langue, donc je vais aller à Montréal. Ouais, non, elle est un peu plus hardcore, là. Donc, mes parents m'ont dit qu'ils
Est-ce qu'on l'a eu?
m'enlevaient toutes mes affaires si je me faisais un autre piercing.
C'était vraiment beau, ça. Avec le petit, pas possible.
Moi, je veux faire l'anneau là ou l'autre ici, mais ça, je... Mais c'est que c'est vraiment épais, j'ai l'impression que ça va vraiment mal. Il y a beaucoup de croquants
C'est
là-dedans.
tellement beau, là. Genre, ah,
Mais c'est vrai, je sais plus. Mes parents m'ont dit qu'ils m'enlevaient toutes mes affaires si je... mes affaires, je n'avais plus d'argent.
sérieux, tu te faisais repasser?
Et comme Steve Côté, il aime pas ça, j'étais comme, maman, no
Steve
offense.
Côté
J'ai
aime pas
legit
ça.
dit, j'ai dit, maman, j'étais comme, no offense, but I don't care what
Côté, il y a
Steve
rien à
Côté
dire.
likes. J'étais comme, c'est bien Steve Côté, mais je m'en fous s'il aime mes boucles.
Il y a rien à dire sur tes boucles d'oreilles.
C'est sûr,
Ça va, c'est
ma mère est genre, mais Steve Côté, il aime pas ça, je suis comme, non, maman,
Steve Côté, il a aimé tes boucles?
non.
Non. C'est quoi ça?
Ma mère a dit le plus de trous, le moins de classe
Moi,
que
c'est pas dans ton nez. Ouais.
moi, je suis comme, maman, c'est pas un tatou.
pas dans votre nez. Ça pourrait être beau, non?
Moi, j'en veux un.
C'est vrai, tu peux le faire là.
Moi, j'en veux un.
Mais là, je trouve que c'est plus beau.
Moi, je veux l'anneau ici. Non, mon amie, elle a celle, le truc avec les 2 boules, là. Sauf qu'elle rentre tout le temps dans son nez pour pas le voir. Genre, tu sais, elle est là. Je suis comme, quand il va take it out, on est comme, parce qu'à l'école, elle a pas le droit, son père, il veut pas, donc il y a juste sa mère qui le sait. Là, quand elle est à couche, je suis comme, qu'est-ce que tu veux sortir? Elle est comme, oh, c'est vrai. Là, elle sort, puis là, on va se faire, là, voilà, donc là, elle a deux anneaux ici, elle a le truc là, puis là, ça va se faire la langue dans 2 semaines.
Mais la langue, je trouve ça.
Moi, c'est comme, mais j'aime les petits anneaux ici.
Genre, c'est fait comme elle, évidemment, c'est plus.
Mais j'aime quand il y a des anneaux, c'est vraiment. Moi, j'aime l'anneau, mais un petit. Mais pareil, ils m'ont dit non. Ils m'ont dit que si j'ai regardé, ils genre me désirritaient. Parce que j'ai fait ça sans leur dire, puis j'ai fait ça sans leur dire, puis ils étaient pas contents.
Il y a rien à dire.
Mais je sais, sauf que c'est eux qui payent. Donc,